All right. I am I am back. Hold on. That's not quite right. There we go. Oh yeah, there we go. And now I am back, and we are stepping through this search function for the first time. Um, these comments didn't really help me understand very much of what's going to come up, so let's just keep going. Okay. Propagate. So we've already read propagate. That's the one that does this. Let's see, did the tail size change at all? Trail? Did the trail... the trail is still empty, so nothing's going to happen there. No conflicts. Okay, so the algorithm here is going propagate. If we have a conflict, we have not read what that does yet. Here we're in the no conflict path. No conflicts. Is greater than or equal to 0 and progress estimate. Cancel until 0, return undone. So here we're doing bailout if we bailout if this is too hard. Decision level. This should be empty, I think. Really? That is weird. I don't know what that was about, but it didn't really show anything useful. Interesting. So simplify. Simplify still runs. Even this deep into the algorithm, which earlier we read simplify, and I oh, but decision level has to be 0. So I think decision level was not 0 there. So, right. So this is using the AND short circuit, right? If decision level is higher than 0, decision level is the name that the SAT solvers use as their counter for how many guesses how many guesses have been made in the process of looking for a way to satisfy the formula, right? So if decision level is 0, then no guesses have been made, and so simplifying there is like simplifying before you've potentially made a mistake. But that only works because of the short circuit here. You would not run simplify every time you got here. You only run it because of the fact that it can... You only run it because of the fact that you haven't made any guesses yet. Now, what's interesting is, I suppose it's possible to roll back to level 0 where you've made no guesses, but where you have new learned clauses, and maybe then simplify would be different? Because simplify would run propagate. Yeah, so it's possible, I suppose, that propagate could use a learned clause to set values that weren't known before. Let's keep going. All right. Um, just double checking. You guys can't hear the background music, right? I don't think so. The the level on the mic is like moving around in a way that looks like it's in rhythm with the music, but I think that's just in my head. Anyway, decision level is less than assumptions. Assumptions. What is Can I, excuse me, Remedy? Can we talk about assumptions? Okay. It might be that Remedy doesn't know how to talk about assumptions, which is frustrating. Okay, so where did assumptions come from? It's in the solver, right? But if I type, what if I type in this? Assumptions, there it is. Okay. I don't know quite how to interpret this. So if the decision level was less than the number of assumptions, perform user provided assumptions. P dummy decision level. Okay, so this is a little strange. So I'm trying to figure out what they're saying here. The assumptions. Okay, so the assumptions are empty here. If there were assumptions, this would apply them. So this does not, to me, look like a optimization feature or a clever trick. This is a parameter being applied, and it's doing like, I mean, basically what you'd expect. It looks at the assumption. If the assumption's already known to be true, then it just increments the decision level, I assume. If if the thing is false, then that means we already have a conflict with things we've learned just through propagation and the assumptions, and therefore we have a conflict. We don't know about analyze final, but then it returns false. And if it's neither true or false, then it's not fixed yet, and so we make that the next thing we're going to fix. So this is just implementing, taking the user assumptions as the first guesses and making sure that those assumptions are applied before anything else. So I assume this should be, yeah. So we've made a new decision and we're going to pick a branch literal. So how does it do this? Random decision, random seed, random variable frequencies. Listen. And okay, so whatever this generates, it can't be less than 0, I assume. Okay. So no random decisions. Activity-based decision. Next equals var undef value next. Does not equal undef. And we do not have a decision for next. I don't think next is undefined, is it? Next looks like it says -1, but, well, that's a variable, not a literal. Okay, so that's undefined. Okay, got it. And the value the value should be undefined because the variable is, and decision so it's looking up into the decision array. I'm not sure what's in there. All right, decision is a VMAP. We haven't looked at VMAP yet. Declares if a variable is eligible for selection and the decision heuristic. Okay. So I assume this takes in well, why would it take in a char? If these stand for variable map, then they map variables to the type shown here. I'm still holding back sneezes all the time if you haven't noticed. Okay. So it's a heuristic, the guidance data structure or something. But that should be true just because our next is still undefined. So order heap, yes, it should be empty, yeah? I can't read it. I don't know why. I'm getting all these cases where it seems like maybe it doesn't initialize the stack at this point. But if I F10, then I've already lost the chance to see anything. It's like one way or the other I end up losing. I end up getting no chance to see what's going on there. But let's see, the heap. Let's go look at heap.h. I haven't read that one yet. So heap.h, what are we doing in heap.h? We got a class k, a class comp, and a class mk_index. So we already know about mk_index things. These are a way for the user of these templates to explain to the template how to cast to a particular type of index. It explains how to construct an index. And it's constructing indexes from integers, which could have already been indexes. It's usually just a cast. That's what we've seen so far anyway. Now, the heap of keys, oh boy. The heap of keys here. What is it talking about? It's a vector that contains keys. Each key's position in the heap. So here we are mapping those k values to integers using this type of indexing to convert the k's into indexes. So what's happening here is sometimes k is a thing that is essentially an integer, but it's like wrapped in a class, and then this helps it figure out how to be treated like a plain old integer. And so this is taking each key, which we have here, mapping it to an index. in the heap. The heap is a minimum heap with respect to this comparator. Okay, so we're talking about that kind of heap. So it's a heap in the sense that it forms a tree of some kind, and the smallest value is always in the root position, and the small is determined by whatever this comparator is doing. And then we are using index traversal of the tree. So if you have an index, we're assuming that the tree isn't just arbitrary binary. It's not just a binary. It's a binary tree. So let's back up and slow down. It's a binary tree with a very regular structure. There cannot be arbitrarily long and unbalanced sides, right? If I have a root and I have 11 total elements, one element is the root. I have 10 more to place. It's going to place them evenly on the left and right side, essentially. It's gonna, I don't know if it's literally balanced left and right that way, but it is gonna be like the next two elements will fill the two children of the root. And I think usually what happens is the next four will go from left to right. So you would get like some lopsidedness on the left side for a little while, but it's like very regularly structured that way. That way, this index manipulation is all you need to go between nodes of the tree. So if I have an index, I can figure out what the left and right index from that index are by doubling and adding 1 or doubling and adding 2, which they wrote this way for some reason. And you can go to the parent by, they're doing it by subtracting 1 and dividing 2, which works. So like if you think about it, this plugs into this and it makes perfect sense. You subtract that 1 off and you divide by 2, which they wrote this way for some reason, and and you get back the original I. In this case, this is actually I times 2 plus 2 is another way to think about it. And so when you subtract 1, you haven't gotten you haven't completely reversed it, but after you divide by 2, the fact that you had an odd number means the extra 1 that was still there also rounds off. So this lets you traverse the shape of the tree. But there's you see what I'm saying? There's no flexibility here in terms of sometimes the trees could be shaped differently. If you have 10 elements, there's only one shape the tree can have. And then the algorithms that control the data structure are set up so that when you insert things, you insert them in such a way that the smaller elements are on top, right? So the smallest element's always at the root. The two things below it are going to be bigger than that smallest thing, and everything underneath them is going to be bigger than those. So the farther down the tree you go, the bigger it gets, always. The children are always larger than their parents. And skipping over the rest of the details, this basically lets you pull out the smallest element in constant time, or I think in log n time, because you also have to adjust the tree afterwards. And it lets you insert elements in log n time, because you have to insert the element at the end of a list, but then arrange the indexes to make sure that it's linked up in the right spot. So basically it's an easy way to throw things into a data structure and then pull them out in terms of the order set by this comparison. Okay. Oops. Don't want to be editing the code. Okay. So that's just checking if it is empty. And then if it is, it did something that we didn't do. Apparently it wasn't empty. Oh yeah, right here, we're already reading stuff off the order. We got here, okay. Okay, so right here it's going to pop something off the order heap, and so we get next is now defined. It no longer is correct to say that next is undefined. And the value of variable 0 is, and I got to get through a couple of these things. So there's our index constructor, is sitting here in this data here, which we can't inspect because either remedy or PDB files aren't sophisticated enough to resolve this on a single line. Brilliant, great stuff. So we don't know. We had no way. We never had a chance to inspect if this came out undefined or not. So that's great. It makes it hard to follow, like, if it was this or this that led to us breaking out of the loop. But let's just say the very logical conclusion is that the new variable we just grabbed is probably undefined. Okay, so if next is undefined, then we have an issue. That's not the case. User poll. Choose polarity based on different polarity modes, global or per variable. If user poll next does not equal undefined, user poll next equals true. No, so we don't have user poll next defined. So if random poll, no. So otherwise we do the polarity. Polarity is a map. So the same thing is going to happen again. We're not going to get a chance to see it. Presumably, this is just looking up to see a Boolean value that is either going to be true or false. Hey, there we go. So those resolve, or maybe they don't. That's not right, you know, because we know next was supposed to be a 0. So that could be wrong too. Sign isn't necessarily true. It could be false. Remedy is just showing us true because it's showing us whatever uninitialized crap is there and rendering it as a Boolean. And since it's not 0, it's true. But we have no way to find out because it's all on a single line again. Okay. Next equals 1. Yeah, sorry about that. Okay, so next pick branch. So we picked a branch, and so this here is a literal, right? We didn't have one come from the assumptions. Where did they first make up next? Next must be a member variable since I don't see it declared. But I don't see it here either. Next. Oh, here it is. Here's the declaration. Next is undefined. We try to get it from an assumption. Otherwise, we use a pick branch, and there's a couple different heuristics that you can enable, and they can be user controlled or whatever. And then New decision level, increase decision level, and enqueue next. Okay, so new decision level tells it to trail limb put to, yeah. So it tells it to remember the index. Remember, the trail is a stack of all the guesses we've made so far, or not guesses. The trail is the stack of all of the assignments we've applied so far. And the trail limb is a stack of the indexes where each guess occurs there. So some of the times we assign a variable, it's a guess. And then some of the time after that, we might assign more variables that are from constraint propagation after that guess. And so the trail limb thing, I'm calling them guesses. The code calls them decisions. The trail limb thing gives us those indexes into the bigger stack where guesses occurred. So we're taking, here's the current size of the stack. Save that as the position where a guess occurs. That's how we do new decision level. And then unchecked enqueue. So it's constructing an L Boolean into the assignment for the variable of P. I don't know what var data is. Make var data. I don't think I've looked at that. Reason level. So unfortunately, this is one of those cases where we're not going to get a good look at it. But from here is, okay, nonsense. That makes sense, actually. Probably there's an optional parameter happening here. So that's just hidden from us there. But it comes in here as max uint, which I'm assuming means, because the cref is a 32-bit integer that indexes into a clause array, essentially. And so here we're what's the current decision level, and here we're saying here's the clause that was critical that led to the propagation of this assignment. But in this case, we're actually applying a guess. So when we apply the guess, there is no clause that's enforcing it. It's a guess. It wasn't forced. So we just use the default, like, nil, or it's not null because it's not zero, but like the non-valid case, the exception case, or whatever you want to call it. And then we push P onto the trail. So remember, the trail is that list of assignments that we've applied. So that's just a list of literals. Okay. So we run propagation again. We got no conflicts. Honestly, at this point, this is looking basically exactly the same as CDCL. The only thing that could be interesting about this is what happens during a conflict. There are, the CDCL I read last time I did this project did not have some of these cool accelerators. Like, it didn't have the trail stack. It didn't have the watchers that let it rapidly find relevant clauses. And I haven't fully finished decoding why it's manipulating the literals inside the clause in such a way, and how the two literals at the front of the clause are special. I haven't made sense of that part of what I saw in the propagation logic, but basically it's the same propagation logic with they've done some work to make it do as little redundant iteration as possible while applying propagation. Now, if we take a step back, what is propagation? Propagation is also already an accelerator, right? So the basic algorithm is that you make guesses and then you check to see if there is a conflict. And if there's a conflict, you go back and you make a different guess. And if you get to the point where you've if you get to the point where you've when you go back, by the way, you only go back so far. You don't go all the way back to the beginning every time because you're not starting from scratch. You are unrolling whatever proximal cause there was to the conflict, right? In order to accelerate that a lot, what propagation does is say, okay, after we make a guess, we're going to look through all of the things we know, and if there are any variables that are not yet assigned but could only logically take one value, we want to find those now. Like if we can easily prove that one variable could only have one value, let's find those variables and apply those now. And then it goes back to another guess. So it goes guess and then propagate and then guess and propagate, right? And the cool thing about that is the things that are happening during propagate aren't guesses anymore. So those are things that if you were to make guesses that were contrary to the propagation, you'd just be wasting time. You'd find a conflict that was obvious and easy to avoid using a propagation technique. So propagation is already an accelerator on that much more expensive guessing, trying everything approach. And then what they're doing here in MiniSat is speeding up the propagation more than what they did in the CDCL I read last time. But what I don't know is when they find a conflict, what do? So the easy thing to do is to just roll back the guess and guess something else, right? Make sure you don't make the same guess twice, but otherwise keep making forward progress. But what CDCL did was take the moment where there was a conflict and learn a new clause. And that new clause would then sit there and influence the way things like propagation work. So when you went to propagate late after the clause was learned, you would have the chance that the learned clause would force something that wasn't forced earlier, and so your guesses lead to better and better propagations as you go. But I don't know if that's what they're doing. So I want to see what happens when they hit a conflict. So it looks like they also they have learned clauses, so it's very possible this is also a CDCL. In which case I haven't picked up a new algorithm here. I've just picked up some optimization, what one optimization for the propagate looks like. So number of conflicts went up, conflict C went up. If decision level equals 0, we're done. That should not be the case. We've made some guesses. I actually wonder... Oh yeah, in Remedy you can't drag the arrow around. Learned clause.clear. Okay. That's just making it into an empty array. Analyze. So analyze is going to take in the conflict. So the conflict is a clause. It's going to take in the learned clause, but that's an output parameter, so it's going to fill that up with the new information that got learned by this conflict. And it's going to take the backtrack level, which is currently 142. And I don't entirely know why there's a backtrack level and why it's so big. Didn't backtrack level... Yeah, it's a local variable. When did backtrack level get incremented? I don't remember seeing it get touched. It's not there. And yet, there it is. 142. It could be uninitialized as well, but I don't think so. Yes, it gets used there. It gets set there. Okay, so I'm going to assume that that is uninitialized still. So the 142 is irrelevant. That's just uninitialized. And the it's being passed in here as an output parameter. And since we're in C++, output parameters don't have the little ampersand there that makes them like obviously an output parameter. Because in C++ you can make reference parameters, and people love to do that to make it harder to figure out what your function does from the caller side, but oh well. Okay. So hold on, I need to take a 5-minute break. I will be right back. Okay. Thank you. My congestion is proving difficult to manage with just tissues, so doing a little more aggressive. Doing something a little more aggressive was helpful. Okay. So let's read this comment. Analyze conflict and produce a reason clause. Reason clause. Interesting. I haven't heard it called that before, but I like that. Preconditions. Out learnt is assumed to be cleared. Yep, we saw it. We read that in the previous thing there. Why they can't just clear it inside this function, don't know. Current decision level must be greater than root level. Presumably they mean 0, must be greater than 0. Like, it can't be the case. We don't analyze. We don't do analysis when our decision level is 0. This just looks like CDCL, you know? I mean, it's clause learning, so unless there's other types of clause learning, I'm pretty sure this is CDCL. Leave room for the asserting literal. Right, conflict clause. Index equals trail.size minus 1. Do assert, otherwise should be, right, fine, conflict. So here we get the clause for the conflict. Remember, the conflict got passed around as an index, but now we want to get to the actual data inside the clause structure. If this is a learned clause that we're having a conflict with, we call bump activity. I don't know what that does, but we didn't hit it this time. I'll leave a breakpoint there in case we get a chance. This is our first time learning a clause, so it's not possible for this to be a learned clause yet. Speaking of which, why don't we look at what it is? It has a size of 3. It is not relocated. It doesn't have an extra. It is not learned, and it is not marked. Okay. J either starts at 0 or 1, depending on if P is undefined. P is a literal, and lit undef. I wish these things could show up in remedy, but I'm pretty sure that's 0. So that should be false, which means we should get a 1 for J. I was wrong. So P is undef. What is P? It's a literal. How is x equals -2 and undefined? Isn't? Oh, right. This isn't using positive numbers and negative numbers for its literals. We should go actually read what the literal does a little bit more carefully. No, not the fat sat lit. That's my lit. Where is the lit for MiniSat? Lit. Where are you? Where are you, lit? Where have you been? There you are. You're in the solvertypes.h. Got it. Struct lit is an int x. How do we construct it? Inline lit, make lit, var sign. Got it. Zen Mystic, hey, I think I remember. Your name sounds familiar. Yeah. Yeah, I'm streaming. So I am reading MiniSat right now. I started this a couple weeks ago, and then I did some other stuff, and now I'm back to this one. I'm learning about sat solvers and what kinds of techniques are used in them to make them go as fast as they can. And right now I'm doing that by reading code. I think after today we'll switch off reading code, but we're reading this one called MiniSat, which was a really successful open source sat solver from 2005, and it's still the one that a lot of references go towards now. Do you know what a sat solver is, by the way? I can give you the primer on the topic if you'd like. Okay, makelet is going to do... okay, so a sat solver is a program for solving the sat problem, and so now I just gotta tell you what the sat problem is, and we're done. The when you have, you're familiar with booleans, right? So if you have a couple of boolean variables, they can be true, they can be false, right? And then say you've got say you've got a list of boolean variables, right? Let's say those are all booleans. You can also make like a logical formula out of them, right? So you can go like x1 and not x2, or not x3 and x4, or x3, and so on, right? And so the idea here is you can, if these all have true and false values, you can plug them into this expression, and the expression comes out either true or false, right? So the sat problem is, what if I gave you this expression, or any expression? What if I wanted to give you a Boolean expression like this, but I didn't have assignments for the variables yet. I didn't know which ones were true and false. I just gave you the expression and asked you to tell me, is it possible to set all of the variables in such a way that the whole expression comes out true? Okay, does that make sense? That's the problem for the sat problem. It's sat as in short for satisfiable. Is it possible to satisfy the formula, right? So that's the sat problem, and sat solvers are the programs that attempt to answer that question posed by the problem. Okay, cool. So anyways, I was trying to figure out, so I'm reading MiniSat, and one downside with MiniSat, it's a well-written solution in the sense that it performs well, or it performed well in 2005 in a competition, and it is still a widely referenced open source solution to this day. What's sad about it is that it's super heavy C++ land stuff, like 2005 era C++ stuff, and so it's been hard to decode a lot of it. But we are working through it to figure it out. And a literal is the name for, in one of those expressions, you have the variable like x1, but x1 can either show up as x1 or as not x1. And we, instead of forming like an abstract syntax tree of the expression, we just either, excuse me, I might need to take a moment to sneeze. We treat each of those like variables as either its positive form or its negative form, right? Its negative form being not x1 and its positive form being x1. And those are called literals, and they're encoded here. There's good reasons to do it that way, but I'm a little confused about how they're encoding it and how their like functions surrounding this type are working. And I apologize if I'm a little off because I'm just super congested right now, and I keep holding back a sneeze or having to pause and blow my nose. Anyway, the makelet function is right here, and it says var plus int of the sign, return p. So they're doing if I give you the variable 1, then this is 2, and then if I give you the positive version, it's probably 2, and if I give you the negative version, it's 3. Right, so they're using the low bit to track whether we're using the negated version or not. And then they return that. So when we look at other things, this is used to negate the literal. Oh man, this whole time I've been reading their code and I didn't even realize they had, like, I keep forgetting that it's a struct with all these overloaded operators and stuff. So I've been seeing the bit negate and assuming it was just an integer getting bit negated back and forth. And no, that's not it at all. It's an operator overload that is flipping the low bit. The XOR lets you put in a literal and a Boolean, and then it flips the low bit if the Boolean is true. Sign is 1 if this was a 1. And the variable shifts it down 1 and gives us the variable in number that we got here. So this could have been var upshifted by 1, for instance. Yeah, okay. And what is the less than for? Less makes P and the not of P adjacent in the ordering. Great, got it. Okay, I follow. So that's cool. So the last one I read used like 1 and -1 for the first variable's positive and negative form, and 2 and -2 for the second variable's positive and negative form, and so on. And while that was clever looking, I was convinced it was probably not the best thing to do at the low level to speed up the operations. And one of the things you have to do is you have to do a sort. And it looks like what they've done here in MiniSat is they've encoded the literals in such a way that a raw sort on integers would actually give you the correct comparison overall. So that's a cool idea. Okay, so let me go back to stepping through it. We determined that P is undefined because P is a literal, and so its negative values are actually not like normal values, which was we were investigating all that to find out. The way literals are actually structured means that they'll always be positive when they are like well-formed, defined stuff. So then this is undefined. J is equal to 0, right? Yeah. And now we look into our clause. So C is our clause right here. We'll use J, the index, so 0. And we get another literal called Q. There we go. That one's valid. We can tell because it's a positive number. Now, I'm not sure yet if there's a way to answer the question I'm about to ask. I'm not sure if odd literals or even literals are the ones that are positive and negative, right? So let's go and look. Where would this be? Dymax. So this is the parser that ingests the CNF structure and sort of sends it all to the solver. And what I want to see is when we read a clause. Where is that? That's right here. When we read a number off of that, here it is using the positive negative trick, and then it is subtracting 1 to figure out the variable. And then, look at that. It just does makelet and then does the twiddle rather than using the Boolean parameter. So if it's the positive version, parsed let is positive, it does makelet, and the default is false. Okay, finally we've got an answer. Even numbers represent the variables which are not represent the literals which are not negated, and odd numbers represent the variables or the literals which are negated. And 0 is actually a valid literal in this setup. So 0 is the literal for the positive version of the first variable. Okay. So then, scene, that is probably a map living in the solver. Level. Level. What is level? Is level local? No, so is it living here in the solver? No. So maybe it's a function. Let's try stepping into it. First thing it's going to have to do is run that var function right there. So that's not what we want. Then it has to run the square bracket operator for the map. So that's not what we want. And then it has to run the var function again. So that's not what we want. And then it can run level. Okay, so level is a function inside of solver. Makes more sense. And it goes into the var data and gets the level from that. So var data, I don't think I've seen that yet. Let's go and read about var data, which lives in the solver. So var data comes with a clause reference called the reason and an integer level. Okay. And then we have a variable map, which stores the reason and level for each variable. It's so strange to me that there's all these separate variable maps with all these things, and then they do actually use a struct for one of them, when they could have done just 2 separate fields here, or they could have done a struct for the whole thing. Like, I don't know. It feels funny. It's fine though. It doesn't matter. It just feels funny. If these are arrays, then this might be like a structure of arrays kind of organization that they're doing intentionally for speed. And then the fact that this is not structure of arrays might be because it just didn't matter and they liked to have it bundled. It felt nice or something. Anyway, bump activity. So again, and they keep calling var rather than just having a local save the thing. Var bump activity takes in variable v and var inc, which we don't know what that means. But hey, we actually have a function with multiple lines, so the debugger can help us. So inc is a 1. V is the variable 39. And that makes sense because we grabbed the Q is our literal was 79. So yeah, when you divide by 2, you would get 39. Yep, that all adds up. And so we're increasing the activity map, saying, hey, this variable here is interesting. Now, what is it that leads to this? So we're looking at what happens when there's a conflict clause, and we're scanning all of the literals in the conflict clause and bumping up their activity. So this heuristic is basically saying, hey, whenever we have a conflict, let's go ahead and say all the variables which have participated in this conflict are like they have they're heating up. They're getting more active. You know, they're more important somehow. Excuse me a moment. Okay. If that gets greater than, what is this? 1e plus 100. Then it scales down. So that's not 100. Is that 10 to the 100 or? I think that's 10 to the 100. So it's saying if one variable has been visited 10 to the 100 times. I mean, it feels crazy, but I guess. We are talking about stat solvers where exponential problem sizes are part of the game. Okay, interesting. Update order heap with respect to new activity. So, yeah, order heap here. Let me go and double check that. I think I've looked at it once, but maybe I'm ready to understand more deeply. A priority queue of variables ordered with respect to the variable activity. Okay, so what it's saying here is that the more active variables are at the top of the heap. So we're probably using this as a data structure to accelerate how we make our next guess. And so it's saying, hey, use the thing off the top of the heap every time. The top thing at the top of the heap will always be the thing with the highest activity that is still available that is still unassigned. And so when we modify the activity level of a variable relative to the other ones right here, we then need to tell it to modify its position inside the heap. Now, what's kind of interesting is I don't know. I would have thought all the variables had to be assigned false for us because we're in a conflict. But maybe var bump activity isn't exclusively used in that path. Don't know. Okay. Now the variable has been seen. So we just mark that as seen. That's interesting. If the level of this variable is greater than or equal to the decision level, which we still don't have an easy way to... Where did my... I don't know where my execution cursor has just gone. That's great. That's great. So if we can get it to run again. Still says it's executing. Something is busted. There we go. Oh, whoops. I wanted to be inside the analyze function, I think. Analyze. And yeah, we were going through this spot right here. So yeah, if I don't step in there, we're fine. Path C, don't really know what that does. The level must have been greater than or equal to the decision level of the whole thing. That's fine. I don't have an easy way to inspect that I have figured out yet. If we go and find the trail limb, yeah, size of 19, and then over here we see decisions 19. Okay, yeah, I got it. So we've probably made 19 guesses, or as they call them, decisions so far, and the variable we're looking at must be one that's at 19 when we see that. So path C, I don't know exactly. I don't know exactly what that means, but if that wasn't there at this decision level, it would emit Q into the learned clause. Let's keep going and see if there's a case of that coming up. So here's 109. If we have not seen it, then we bump its activity, we mark it as seen. So the seen thing here must be there to prevent us from it's there to prevent us from, yeah, there's what I was looking for. It's there to prevent us from visiting a variable twice during a single analyze, and then at the end of analyze we zero out all of those. So they're seen, they're kind of local to this function, but they are per variable. Okay, do any of these ever hit, or do we just end up here? There we go, we found one. So Q, 178, does actually find, oh, we want to keep that in case we find one that does that later. Q must have a level that is lower than 19. So it goes into the learned clause. So everything that's going into the learned clause is from before guess number 19. The things that are in the current, anything in this clause that had a level of 19, which we know at least one thing is going to have to because the conflict has just occurred. If there are more things that are at that decision level, then they must have been propagations from the guess number 19. And finally we found something in here that wasn't a propagation. Now we're saying, okay, this one we can keep. Okay. Index 28. Trail. So while we've made 19 decisions, we have 29 assignments in our trail. And now we're stepping backwards, looking for any of them that we have not seen, that we did assign. right? We're going backwards. So where did index get assigned? Index started here. So index started at the as a sort of reference to the last assignment we've made. We then say, hey, can we grab the literal off of the trail at that index, convert that into its variable form, and then see if we've seen that variable yet. And eventually it should stop. There we go. So at index 28, because it used index 28 and then decremented, so at index +1 or index 28, we should find an interesting literal. And now the new conflict right, so it's the reason on that one. So when we have a reason, it's because we assigned this during propagation. So there's some clause that got critical, and that clause was used to propagate a constraint onto this variable. And so now we're grabbing that clause. So clause with the ID of 72. And then we mark P as not seen. P is the thing that we found here, but we already know that it's not seen. Why are we marking it as not seen again? How? I don't know. That seems off. So we grab the clause for that conflict. That clause should not be learned either. And then we go and we look through that clause same way as we did before. And the index doesn't get reset, so it just goes back some more. We find another one, we get another conflict clause. So we're gathering up all of these variables here, all these literals here that we find with the following properties. One, we're looking at all the variables we've never seen before. So we don't consider a variable twice. So we don't put a variable here twice, or a literal. Rather, we never put two literals on there that are both for the same variable. And we're only interested in variables who are decided after decision level 0, since decision level 0 is the one we can't roll back anyways. Then, heuristics, we bump the activity level, and finally we mark this one as seen, so we don't visit it again. And we either increment path C, or we add that Q, which is the literal. So the literals that end up here inside of outlearned, that's what I want to talk about. They are deduplicated by this part, and they are all less than the current decision level by this part. And then here we grabbed another one. It hasn't been seen yet, so we set up to use that one and continue from there. Path C is greater than 0. Path C minus minus path C plus plus. Oh, interesting. I don't know what path C is doing, but it is controlling the loop. in some way too. So this looks to me like it is implementing the same thing as the CDCL I learned last time, but it's doing it in a much tighter way. Before, it was doing this whole like thing where it would take two clauses and resolve them into a new clause, and then take that new clause and resolve it with another clause until there's like iterative clause resolve logic. This appears to be a tighter algorithm for achieving the same output, is my guess. It is understanding. Yeah, that's a local. Now it makes more sense. So all of the variables that were decide either guessed or um, received their value from propagation during the current decision level cause this to go up, and they don't go to the learn clause. But all the earlier variables, and if we looked at what that conflict resolution thing was doing, it was basically doing the same thing. It was causing, every time we had a conflict clause, it was looking through the variables and saying, hey, if we have a variable with this property here, look at its reason clause and use its reason clause together with the original clause to put through resolution. And during resolution, it would eliminate those variables that were from this current decision level. Thank you, Niner Delta. I paused to blow my nose earlier and forgot. Anyway. Also, welcome. So, analyze to clear. What is that? It must be a member, right? There it is. So we learned that clause. We copied it into this one. CC min mode. So here we're going to simplify the conflict clause. I don't know what that means yet. IJ equals 1. I is less than the size of the learned clause. Okay, so here we have one of those loops where we have a read pointer that's running ahead and a write pointer, and they start off together at the beginning, and as the read pointer advances without advancing the write pointer, we are basically dropping whatever we advanced past without writing backwards, right? And then we take a look at the learned clause and we say, hey, what was the reason for this particular variable? The reason is a clause and that can be undefined if we just made a guess at assigning that variable rather than getting forced into it. But I don't know what lit redundant is going to mean. Or if not, we lost the okay. Remedy's having some difficulties with this program sometimes for some reason. Okay. What do we got here? Nothing. Nothing. If not lit redundant. Okay, we're gonna have to look that up a different way. Okay. Alrighty, so check if P can be removed from a conflict clause. Scene undef, scene source, scene removable, scene failed. Assert scene P, scene undef, scene P equals scene source. Right, so at this point we've either got this value set to this map here is cleared to 0 initially. And then we poke 1s into it when we see things. So we shouldn't have seen a 2 or a 3 in there yet. That should be impossible. That makes sense. Oh, damn. Okay. And it should not have an undefined reason. Yeah, okay. Oh man, the congestion is not letting me it's not it's I don't know how to describe it exactly. Just like completely taking over my ability to think once in a while. Okay. What are we seeing here? So the P is the one we're trying to see if it's redundant. We take its variable, we grab its reason, which we know is not undefined, and so we grab its clause. Then we take the analyze stack, which we haven't seen yet, but that's a member variable of the solver, and we're just taking a local reference to that. We're clearing it out, okay? So it starts off empty here. We do I don't know why. It must be that the first one we looked at did have an undef here, and that's why we didn't run through it. So let's actually just see if we keep going. No, it just skipped on. It didn't even run this function. I want to understand that function before I advance any farther, so we will have to read it straight up. So I is less than the size of the clause. When does the loop ever end? If you, I see. If I is less than the size of the clause, checking P parent L is the L is the literal that we got from the clause that so the clause is the reason clause from the literal P. So literal P gave us a reason clause C. We're iterating the literals of that clause. So that'll include P, but it'll include other literals too. And we put those into L as we iterate them. Variable at level 0 or previously removable. Right, so here the variable's at level 0. Scene equals scene source, we've seen it. Or scene equals scene removable. So it's removable. Then we continue to the next one. Check variable cannot be removed for some local reason. I'm having a hard time with this part of the code. So the literal's reason is undefined, or if the literal's variable has this failed state. Then, so if it's in either of those cases, then shrink stack lm, we push that onto the stack. What is shrink stack lm about? There's so many things here. Okay. L. Okay, so we must have a stack of these shrink stack things. That must be what the analyze stack is. Yeah. So the analyze stack is a stack of these things called shrink stack elements, which contain an I integer and an L literal. And so we push onto the stack 0 and P. We scan the stack and see if anything on the stack is undefined, then that thing is failed. Analyze to clear it up, push. The literal from that. What are you talking about? What are you talking about? You're looking at the literals from. So I have no idea how to interpret this still. We got to this because we were reading this code here, and it's trying to simplify the clause that we've learned. And one of the ways it simplifies is by saying it can erase something if its reason is an undefined clause. So if it was a guess. Let me think. So a clause, a normal clause we don't want to modify, but a learned clause is just a bunch of variable or literals ordered together. If you erase random things from that, it can't actually make the correct answer change to the question change, right? Because the variables that are missing will be free rather than constrained, but they're already inside of a learned clause. And a learned clause is already something whose variables or whose structure is like, it can't be the case that this modifies the answer to the question. It can't become impossible to satisfy the whole formula because of a learned clause. And erasing variables from a clause only makes it even easier to satisfy. So it's already guaranteed that the learned clause is satisfiable if the whole formula is satisfiable. And so erasing things from it maintains that guarantee. So we don't have to be precious about what we erase, right? We could erase things for strategic reasons. There's no logical downsides to erasing them. Maybe just a performance downside. So it might be saying here that things which were included that came from an undefined, like whose clause was undefined, those might be unhelpful to keep. But why would we remove things that are not redundant? Why wouldn't we remove things that are redundant? Right? It seems like if you had a thing that said, if this is redundant, then remove it, I would be on board. But this is saying, if this has an undefined reason clause, or if it is not redundant, that is, usually a good thing. But in this case, it means we're going to remove it. Oh, wait, no, it doesn't. It means we're going to save it. I'm reading it backwards. Okay, so if it's not redundant, then we save it. If the reason is undefined, then we save it. Okay. So we're happy with losing anything that is redundant and had a reason clause. And this function lit redundant is somehow figuring out if it's redundant information in a way that I don't understand yet. So if this returns true, then it's saying, yeah, you can remove this from a conflict clause. Let's see. Okay, so it returns true if the loop gets to the end. It only returns false here. And it updates the state of this. So this is not just a check. This is a big chunk of logic. It's kind of overwhelming how complicated the organization of this is. Okay. So let me think. I think what I do is I put a breakpoint inside this function, and if I want to learn it, I just need the debugger to hit it. So 394 in solver. Let me know if we ever hit that. Okay. Okay. I forget what search is about. Search for a model. This is this one, right, with the crazy comment. Search for a model, the specified number of conflicts. Note, use negative value for no if conflicts indicate infinity. Don't know what it's talking about. Number of conflicts or something like that. Search. Okay, search is the main loop of the solver. The rest of this is like wrapping. Okay. Excellent. So we found a new conflict. That's what's happened. So it goes in there. Generates the learned clause. Which is a couple of new literals. Didn't eliminate it didn't eliminate any. We skipped this part before. Find correct backtrack level. Find the first literal assigned at the next highest level. Let's see what it's talking about. I equals 2. I is less than out learned dot size. So we skipped the first two literals again. Those first two literals are significant in a way I don't understand. Swap in this literal at index 1. So we grabbed 160. We stuck it right there. 82 is right there. I think that left it the way it was. Find the first literal assigned at the next highest level. We went over each literal. There was no. It was empty. If the level is higher than the level of the max, if the level of the one we're looking at is higher than the level of the max, that becomes the new max I. Got it. So we're looking for the literal in the learned clause with the highest level. Swap in this literal at index 1. Out beta level, probably. And again, it's this confusing thing where it's now saying that the level it's recommending to roll back to is the one, is the highest one in the learned clause. So it's not even talking about unrolling, because if you unroll to that level, you don't even unroll. It's like it's the level you roll back to. If you roll back to level 10, you keep all the decisions from level 10. You keep all the effects from level 10. That's very confusing to me because I would have thought that you would need to undo at least you don't need to do undo level 10 as well, because clearly one of them must be a wrong assignment. And then we clear out all the scene variables. And so we're going back to level 20. We're at level 33, so we're rolling back that far. And so we are unassigning So we are unassigning variables, I think. Right, because we're saying assigns x undef, and then the polarity of x is set to the sign of the trail. and we insert X back into the heap, I assume. Then we roll the Q head back to the correct spot to continue from that decision level. We shrink the trail and the trail limit. Decay activity. So what is that doing? var inc. Oh, interesting. Var decay. 1 divided by var decay. So it's incrementing. It's slowly growing how big the var inc is. When I first stepped through it in the first iteration, that was a 1. So it's a little bigger, which means that when it sees variables in later conflicts, those variables heat up a little more than they did when they got observed in early conflicts. Decay activity. Clause decay. Oh, so clause has an increment, and it must be decaying. Yeah. Okay, so when we say decay, I usually think of taking something and shrinking it down by a certain amount. But I think what they have done is they've said, yes, we want you to be able to think of it that way. But if we have, 100 variables and we want to shrink all of their activity level down every frame or every loop through every time we deal with a conflict or something, that's a lot more work than if we just increment how big the increments get from then on. Right? It's sort of the same effect. If they're all the same size relative to one another, then instead of decaying 100 variables, we can inverse decay the incrementer, and so when we increment variables in the next round, the ratios will be what they should have been, but we didn't have to scan across all the variables. That's why it's divided by the decay. That makes sense. Good thinking. Word size adjust count -1. I see. So this is like a counter here that, every time it hits 0, it's going to print some stuff. And then it's also going to slow down how often it prints with a sort of gradual exponential increase. Okay. More conflicts. Do we ever hit that other breakpoint I wanted to hit? Here we go. It took a couple of conflicts, but we have a chance to find out about this check. So this, if this is true, short circuits this, right? So that's why it's not getting hit very often, because we're just saving variable. We're choosing to save variables just because they're all variables that have no specific clause reasons. And I kind of think that makes sense early on. A clause reason occurs when, or a reason clause occurs when we do variable propagation and a critical clause is discovered, and then we use that critical clause to decide how to assign a value to a variable. When we are early on, we probably have more guesses than constrained variables, right? So it's not surprising that we don't find very many of these. But eventually we found one where we had a literal in our learned clause that was actually set by a constraint rather than being guessed. And so we want to now see, is this redundant, right? And how could it be redundant? Well, I'm not sure. The obvious way is if it's a duplicate inside of the list, but that's already been eliminated. It could also be redundant if there's another variable in the clause already that communicates all the same amount of information. So basically, having too many variables in our clauses makes them less likely to go critical, and therefore we get less zooming ahead from propagation. And so removing any variables that aren't contributing much from the clauses that they live in is good, but especially if we can eliminate any variables that are literally they have to be true given other arrangements in the clause already. Like they literally communicate the same thing as something else in the clause. So I suspect that this is about looking at the other literals in the clause and seeing if there's a relationship between them that somehow reflects that P is redundant to something else in the clause, and then we can eliminate P. I don't really know how it's figuring that out. What it would even, like, what the structure. I don't even know what I don't know what the structure of that would look like if it was something you could do, and two, I don't know how it's checking for that structure. None of that makes sense. So we know that the analyze stack gets renamed to stack here locally. The analyze stack is a stack of these shrink stack element things, and all we know about that is that it contains an integer index and a literal. All right. Then we start iterating. If our iterator is still inside of the clause, then we grab the literal from the clause. The clause, by the way, comes from the P we're trying to, the literal we're trying to reason about. So here's what's happened. Here, we already checked that there is, in fact, a reason clause. Now, the reason clause won't be the learned clause, right? We're not talking about the learned clause that we're modifying, right? We built a learned clause earlier, and now we're trying to modify it, simplify it. That's not going to be the reason clause, because that one's still under construction. So the reason clause will be the clause that was used during propagation to fix the value of P. Now we're going to look through all the variables that appear in there. And at first, this is possible. We might have already seen some of those variables, in which case we skip them. They might also be fixed variables, in which case we skip them. But if the literal is neither a part of a fixed variable or a variable we've already seen earlier during the construction of the clause, then if that L was a guess, then P can't be removed. And if L has the failed state, which we don't know what that means. We don't actually know what this means. We've never seen something assign that, and we've never seen something assign this. We don't know what that means. But if it was in that state, whatever that will mean, then what you would have done is you would have pushed something onto the stack, with I equal to 0 and the literal equal to p. And you would have scanned the whole stack to put fails on all the things in the stack that are undefined. Really, we scanned the whole stack? That seems crazy. And for each of those undefined things we found in the stack, we mark it as failed, and we put it in the toClear list. Now, remember, the toClear list got set up here. This is a member of the class, so it carries over silently. And we copied the original version of the learned clause there. And then we go ahead and say, no, you don't need to keep this one. Or you do need to keep, no, this one is not redundant. We say this one's not redundant. So it's not redundant if the variable is guessed. It's so hard to understand. I could really use a picture for this too. So this might be a third place where a picture will help. But we're looking at P, and we're looking at the clause that forced P's value. We're looking at the literals inside there. If any of these happen, we get out first. So if this has not happened, and this has not happened, and this has not happened. So we must have an undefined scene or a failed scene. And it must not have a level of 0. So it's derived from a guess or a propagation off of a guess. Then it's possible that it's not, that this literal will prove, this literal L might prove that P is not redundant. And the way it would do that is, one, it might be a guess. And guesses which weren't already seen and which weren't fixed. I just don't understand. There's too many things here. Guesses, so we had a guess. It did not show up anywhere inside the clause because it would have been seen if it was. And it's not a propagation, it's literally the guess itself. But that guess appears inside the clause that forced P. Then, because we didn't see L, and because L is a guess, not a propagation from something else, we now know that P contains information. I don't get it. And we could also learn that this is not, if it's already marked failed, things get marked failed right here when we iterate the whole stack and make sure that everything in there that was undefined is marked as failed and put on the toClear list. Doesn't mean anything to me still. But let's keep going, see what else we might find. We then push IP here. So if we didn't return false there, we take I, which is a 1, and P, and stick it on the list, on the stack. We set I back to 0. We set P equal to L, the literal we were looking at. And we grab the clause from that literal and keep going. So this is some kind of iteration. I think if I start drawing the data structures of clauses and literals and how they relate to each other, this might start being easier to visualize what this is doing. So yeah, this kind of just feels useless. Like we just marked some stuff as failed. We determined this is not in fact redundant. I'm not getting anything from looking at this section of the code. So yeah, let's say that's enough MiniSat. I've got a little bit more time to stream today. I'm gonna take a minute and try to get my drawing tablet working, and maybe we can take a little time and try to figure out how to draw a SAT problem instead of reading the code, because I don't think I'm gonna get any farther on some of these dead ends that I've hit. Give me a moment to mess with the tablet. All right, we're in business. We've got a drawing tablet up and running again. So let's rearrange a little bit, move that over here where I can use it. All of that needs to go live somewhere else. Okay. Let's try this. We want Milton. Whatever this is not what we want. New Milton canvas, yes. Let's call this SAT. Let's see here. Background color. Let's make it like that. Nah, that's annoying. Let's make it like that. Okay. Draw. That's no good. That'll do. Okay. And let me see if I can remember my controls for navigation a little bit before I get too far here. Zoom level ranges from 0.05 to 16. So there's a good starting point. Okay. Actually, that would be best. Okay. So when you have a SAT problem, one way to look at it is we could look at it as the clauses, right? Because we're in conjunctive normal form. So each clause is like a list, like that maybe. The pen calibration is pretty far off. Maybe I should try to fix that first. See if I can remember how to do this. Wacom tablet properties. Calibrate. Okay, 1, 2, 3, 4. Okay, that should be pretty good. All right. Okay, so we have these clauses things, and we have a bunch of those, and then we have each of these. We might want to think of it as like there's this list of variables over here. I feel like it's important to really capture that there are a lot of those. And then we have a bunch of variables over here. And with each variable, I kind of want to have like a sense of like a positive and negative pole to that variable, right? Because each variable can be in one of two states. So each of these little pairs of loops is one variable. This is the positive, so true version of the first variable. This is the false version of the first variable. And now what we have is clauses are like, well, let's draw clauses oriented differently so that they will fit this picture a little better. Come on. I might need to tell Milton I want a bigger eraser. How can I do that? Size. I don't know. I don't know if there's an easy way to do that. Well. So a clause, we could think of it as a guy like that. And there are these links. So each box in a clause links to exactly one bubble on the list of variables, right? Right, so we can start to capture this structure, the pattern between clauses, which is that they can be similar to each other and different from each other, and related to each other by the way they relate to the same variable and by the way they relate to the positive or negative pole of each variable. And in an interesting problem, there'd be enough clauses to really give lots of references to all the variables. So like in this case, it starts to be easy because we have a variable here that is only used on one side, one of its bubbles. And we have another variable here that's only used on one of its bubbles. So we just start picking that, and we're already done, right? But when both sides of the variable are referenced, then it starts to get more tricky and more interesting because you can only pick, the assignments that you pick are an assignment. An assignment is like this. You have one value for each variable that you get to choose, and you have to point that at one of the two bubbles of the associated variable. And so what you want is the links. You want so that when you pick an assignment, all of the clauses get hit, right? If we follow from this assignment to here, we then find, oh, that clause is covered. From here, that clause is covered again. Here, that clause is covered again, and oh, this one's covered. Here, that one's covered. Here, that one's covered again, right? So this assignment works. And if there are a lot more clauses than variables, then it can start to get pretty interesting. Because there are trade-offs to choosing the top or bottom polarity of each variable, right? Okay, so now what I want to try to do is I'm going to go back to the code for a moment, and I'm going to try to pick one of these. Let's start with trying to just think of which one to start with. I have three different spots. I could work on this redundant check. I think it'd be a little bit better if I started with, where is the search function? I think it's going to be in a CC file and not an H file. So maybe like solver CC, search, search function. Here we go. This is where if we have a conflict, right. So if we have a conflict here, we generate a learned clause, we do a backtrack, we stick the learned clause into the list of learned clauses. I don't know what attaching the clause does, actually. I haven't read that part. So that puts some stuff into the 0, 1 thing here. So it says if we choose the alternate value for C0, then we want to, then that is going to put pressure on C1. And if we choose the alternate value for C1, that puts pressure on C0. That's essentially what's written here in very, very loose terms. Okay, so every time we attach a clause, it does this watcher thing. So maybe let's draw a picture of the watches. Yeah. Okay. So we make this sort of orange. So let's look at what the watches might look like if we try to draw them. Okay. So watches get added whenever we add a clause, right? We attach a clause. We can see here, attach a clause gets called in 2 places, 3 places, right? But we're not actually looking at the simplifying solver yet. So this one is a part of add clause underscore, which gets called from all these different variants of add clause. So I assume, like if I go and look at add clause, I assume that gets called, where does that get called? No, that's not it. Somewhere, I assume, add clause must be getting called oh, these look like maybe they're for constructing these manually, because you see you've got like ones for a certain number of literals just to make them convenient, probably. Let's go back to the Dymax real quick. I want to see when it read a clause, it would build the clause up there. What would it do with the clause when it was done? Okay, so it's just calling the add clause underscore, which is interesting. Add temp. I don't know why it all goes through that add temp. Why it's like gotta go through that add temp thing. Feels funny. Anyway, so yes, add clause does in fact get called by the thing which generates the clause from the input file. And add clause calls attach clause. So when it When it takes that in, it does some processing on it. It sorts it right away. So all the clauses are sorted. That is interesting. That's big to know, because I've been wondering what's specifically why there are parts of the algorithm that specifically give special meaning to the 0 slot and the 1 slot. And if they start off sorted, then maybe that's a part of the significance. Not sure how yet, but it seems related, since that determines what will be in the 0 and 1 slot early on. I should also track down what the sort rule is there. It might not. I think it's just going to be comparing them based on literal values, and we looked at that before. Yeah, that seems pretty likely. Return true value. PS dot shrink I minus j. PS dot size equals something right here. PS dot size equals 1 unchecked enqueue. PS. Okay, propagate. CR. CREF undef. Okay, so allocates that, pushes it onto the initial clauses of the problem, and attaches it. And the attach clause is the thing that creates the watches. So it is true that all the clauses in the problem have gone through this processing, which is what I was trying to verify. So now that I've verified that, what I want to do is basically say, what if I drew a picture of what watches look like, assuming that every clause has undergone this logic, right? Well, let's check something else. Okay. So I've already sorted my clauses, right? The each clause here, I have lines that cross, but there are cross clauses. If I look at just the first clause, its lines don't cross. If I look at the second clause, its lines don't cross. So this is essentially already sorted, my picture, right? It doesn't represent what an unsorted clause would look like, which is good, because that means that that's good. It means that I already have that matching up with what the picture is going to need to look like. Because what's going to happen is we have a list of watches for each of these bubbles, right? For each variable, there's a positive polarity and a negative polarity, and each of those polarities gets its own list of watches. Now the watches are a pointer to a clause and to a literal, I think. A literal being one of the polarities, as I'm calling them now. Man, I've never experienced such strong spring allergies. It's rough. Okay, so right, so the new watch goes on the list for the negation of 0 and 1, the first two spots. up here you can see before we don't do this to everything. If we have a zero sized clause, we're screwed already. If we have a one sized clause, then we put that into the forced assignments. So basically a clause with one literal in it fixes the value for the variable, right? If I say I have all of these clauses anded together, each clause has to be true, and then some of those clauses have just one literal in them, then there's only one way to make the unitary clauses true. It's basically propagation applies to them immediately. And you can see they're even going in there and just saying like, yep, go ahead and run propagation. We enqueued the thing that needs to get propagated. Go ahead and propagate it right away. If you add a clause with one variable in it. Then if it's got two or more, it goes down here, and so this makes sense. Yep, that's what I was thinking about. So we take the negated version of the first and second slots as the place where the list gets appended, and the new list has a pointer to the clause that generated the watch and the positive version of the other variable from the clause. Okay? So that's what we want to look at. So, first variable here, our first clause here, let's go through these one at a time. So we're looking at the first clause. So the negation of this variable will contain a, let's label these over here. So this is going to be clause number 1, 2, and 3. And these can be variables A, B, C, D, and E. So the watches start to look like this. This here, so we take that clause there, we negate the first one. So it's not positive A, it's negative A. It gets a pointer to 1, and what is this? Not B. So I'll write B with a line above it for not B. So there's our first watch. It's on this guy. Now this one says, okay, so positive B gets a watch for 1, and the negation of, no, the positive version of this, so positive A. All right, and that's it. We just do the first two. So this has a watch on not A. So it's going to insert this has a link to not A, so it's going to insert a watch there. So it's got a 2, and what is this? Positive D. 2D. And this has a positive D. So this goes on the negative D line. We get a 2 and a negative A. Okay. And then the third one. We get a, okay, that's positive B, so this needs to go live on negative B. We get a 3. And what is this? A negative C. And this lives on negative C, so its watch goes on positive C, and it gets a positive B. Okay. So that's what the watches look like. And I haven't really done anything new that I didn't know about, but it does make this more intuitive feeling. I can picture a little bit more of it now. Let's modify the layout a little bit. Watches. Right? Okay. So So they kind of exist in these pairs. For each clause, there's a pair of watches, right? And the watches live on two separate, the pair of watches lives on two separate watch lists. Each one contains the literal that you need to find the other watch list except negated. So like here's 1 and it says go to negative B, but if you went to positive B, you would find the positive A, which of course would take you to the wrong spot because you need to go to the negative A to find the other one, right? So they're paired off in this way where they have all the right information, but it's all like flipped by 1 in the literal column, right? But they have the right information to find the other member of the pair. So that's the data structure. I'm a little confused about like what's the significance of that data structure still. And maybe for that, what I need to do next is go and look through the algorithm that was using watches that I first read. So the first one I read that was using watches, not generating them, but using them, was over here in the solver. Solver CC. Let's see, watches. Yeah, here it is, Propagate. So I've got maybe 15 minutes, maybe a little more. So let's try to draw a picture of what Propagate does in the time we got left. All right. What have we got? So I'm not going to try to draw this part. This is just saying what literal do we process next, and it processes them in the order that they are sitting on the trail. If we go and look at that, I think it's like Unchecked enqueue, I think is the name of it. I suspect that this is the one. Yeah. This is assigning a variable and pushing it onto the trail, right? Which is a part of assigning it. So the trail and the assigns go together because they are just different data structures tracking the same larger fact of what things have been assigned. We then use the queue head to grab the next one we're going to process. We use watches lookup. So what watches lookup is doing is it's taking P, and that P is one of these literals, and it's grabbing the list of watches sitting on that. And then it's going to iterate the watchers using I and J. End is just there to tell it when to stop. Now, this part makes perfect sense now. So what it does, let's walk through this. Clause, let's say that we, what's an interesting one here? Not B. Right, so here's an interesting one. If we assign the variable not B, right, so we assert let's say we assign not B, right? So this is now a fact, not B, right? So what happens is, actually let's write it this way. Instead of saying assign, let's propagate not B. Propagate. Okay. Let's propagate not B. So it grabbed not B off of that, looked up the watch list. The watch list is this one. So it grabs a pointer to the following watch list. Right? Grabs that. And then it's going to go, okay. Now that I have that, let's iterate them. So the first step it looks at is does this have a blocker? And so blocker means we look and see, is not C already true? And we haven't propagated anything else, we're not assigning anything, so we'll say no. That's not true. So that's the pair that went with this. Now this makes more sense. 3 is the clause. 3 is uniquely... 3 is in the position that it cares about both the variable C and the variable B. And so when we assigned B the value of false and propagated that fact here, what the watches are doing is they're saying, oh, well, when you do that, you're putting pressure on clause 3. And in particular, you need to look at clause 3 because it relies on variable C. Now, variable C might already be set up to make clause 3 happy, right? So you might look and see, hey, is clause 3's blocker, which is what they're calling it, I don't know why, is the clause 3's blocker already true? If it is, then there's nothing to learn here. If not, then what we do is we go look at the clause that the watch references. So looking at clause 3, we are grabbing that clause and we're taking the negation of the literal we're assigning. So we're looking at positive B. Looking at positive B. Yeah, we're looking at positive B But positive B is not going to be in clause 3. What am I missing? We assigned not B. We use that to look up the watchers. Not B contains this because clause 3 contains positive B. And so we took the negation of B and put not C there. So then not B, you're saying not B is either in the first or second position of C, or of clause 3, but that's not true. It's, oh, no. Okay, we have not B here. We propagated it. The negation of not B is positive B, which is in clause 3. Right, okay, that makes sense. So we found clause 3. We know that one of the two special spots in clause 3 must contain positive B, because this is the watch for clause 3, and they come in pairs. So there are 3 pieces of information to each of these. Which clause number? The first literal and the second literal, right? Those are the 3 pieces of information. Clause number, first literal, second literal. Then we organize that information in lists attached to each of the related literals' negations. So we have 3B and not C here. Well, 3B and not C are form that triplet that we would store that here and here, except when we're inside the list for not B, we already can deduce the relevance of B and its polarity in the triplet. So it's not interesting to store, it's not useful to store that extra information about the triplet. And so these are like triplets that have a piece of redundant information chopped off as we are storing them inside of relevant lists, right? So we propagate not B, we come here, we find this list, it tells us clause 3. Now we know clause 3 must have a positive B, since we found this by looking in the list of not B. The finished version of this triplet must be 3, not C, and positive B, because we found it in the negative B list. And so then we go to 3, well, what do we do? Let's go read the code. We go to 3 and we make sure that the positive one, that the positive B is in the second slot. So it's going to actually go over here, look at clause 3 and go, I know one of you two is a positive B. And it's going to swap clause 3, 0 and clause 3, 1. It's going to swap these two. Thereby putting the positive B in the slot 1. Okay, that much of it makes sense. And it makes sense now why they can guarantee that that is true from the fact that the watch exists. Now, if the 0th watch is true, then the clause is already satisfied. Isn't that the same thing as saying if the blocker is true, the clause is already satisfied? First here and blocker here should always be the same, I think. Well, let's ignore that. This might just be a little quick optimization. And yeah, I mean, still though, they're calling it the blocker inside the watcher. But I think this watch We know it has the same clause reference. I'm convinced that must be the same exact watcher as this one that we are iterating on already. Maybe there is a different case, but from what we've seen, from all the code we've seen so far, that's guaranteed. But if there are other pieces of code that we haven't analyzed that change state in ways that are invisible to us right now, then it would not be correct to say that it's guaranteed. So it's not really guaranteed, but from what we've seen so far, unless we see something that changes the rule, that these exist in pairs referencing the first two slots, that's just a little bit of redundant naming for the same thing. So then we make a new watcher. It's a copy of the first one. First is not equal to the blocker. Okay, so they're saying that actually is a possibility. I'm not sure how yet, but they're saying first and blocker don't have to be the same. So if first and blocker aren't the same, we do this logic. If they are the same, they are aware that that's already been handled. But if first and blocker are different, so we're going to be on the lookout now for how that's possible, then we check the value of the first thing. The value of the first thing is true, then we save this watcher and continue. So the new watcher here could be different, but we're updating the watcher to have the correct new first element, essentially, right? So if it's possible that the blocker and first aren't the same, then what we're really achieving here is reassigning the blocker of the current watcher to be whatever is there now. Because once upon a time, it was the first thing in the clause, but it maybe got shuffled somewhere else, and now this first thing is different, and so we want to update the watcher pair, right? Or triplets, or the pair of triplets. Okay. So that makes sense. We are earlying out once if we have a blocker here that's already true. We are earlying out again if this first spot is already true. And in that case, we are updating the watchers so that they once again reflect the first two slots of this clause. Then we look for a new watch. So this part gets interesting. So now we scan. Now we scan the remainder of the clause. So from index 2 to the end. And what do we do there? Let me read the code again. So in here, if the value is not already false, so it's either true already or it's undetermined, then if we find another one which is undetermined, we're swapping it in to the beginning of the clause. So we got to keep in mind, I said that they're sorted and that was significant. I'm not so sure that it's significant. Because of the fact that we swap the clause numbers around a lot, it actually feels like it's got to be insignificant that they're sorted, except that at the beginning of the algorithm, we're more likely to have the watchers all focused on the same variables more often, right? Like the earlier variables will get a little more attention from the watch system early on because of the fact that the clauses come in sorted. But by the end, they won't be sorted anymore because we do like swapping on things in place. So that's important to keep in mind. But here again, we're swapping, right? So we scan the clause, and if we find something which is not already false, we swap it with position 1. And then we push a new watch into position 1 right here. Now, the reason that is safe is because we've also erased a watch here. Right? So this is all kind of subtle and hidden. Here it erases a watch. If it goes down this path, it creates a new thing to fill the slot that is very similar, but not quite the same watch. It's updated. But here, it's looking for a whole new one. So instead of creating a new one here and then moving on, it's trying to create a new one here and then moving on. So anytime we erase a watch here, we end up trying to replace it in one of a couple of ways. So if we took this out, then we're done. If we take this out, it'll be because we found something that was not already false. In particular, not a variable, but we found a literal that either evaluates to true or indeterminate. And we swap it into the watch position. And then the one we erased by not saving it by not copying it forward is the watch with This is confusing. I need to draw this. Okay. Okay. So we're looking at the other indexes. Let's say here, this is not false. Right? Negative D is not false. It's unassigned. So one sec. Okay. So we look at this one. We're on clause 3 here. We're on clause 3 here, and we're looking at we're looking at index 2, and that's this third slot, right? And that points at the negative of D. So we find that is not evaluating to false, and so we're going to swap This is leading to a swap of clause 3.1 and clause 3.2. So that gets a swap. And so if I drew out what this looks like after these two swaps, we started with positive B here, and we're going to end with it down here. We started with negative C here, and we ended with it on top. And so the final one, which is negative D, must be here in the middle. So there's our new arrangement for the clause, right? Swap here puts B and C in the opposite order with negative C and then B and then negative D. And then swap here swaps the negative D up one and the B down one, so we get negative C, negative D, B. And then the watch that gets erased is this one, because that's the one we read. And we didn't replace it. Well, that's not true. Hold on. Hold on. I'm kind of skipping ahead here. Here, we set up a watch for this clause that looks at the first thing, which we just swapped in with the one that was in position 1. And so that's actually a watch for 3 not C, right? Have I made a mistake? We grab I. I's blocker is not C. That doesn't block us. I clause ref. Clause takes the clause ref. The variable we started with must be in one of the first two slots. We sort it so that's in the second one. And then we increment. And that increment means we are now on the list of watchers pointing at the spot. The read location is now one past the current watcher. We've consumed this watcher and swapped, put the P in the right spot for it. Then we look at what's in the first slot of the clause, and if that happens to be true, then we just save that out into the same location we would have written if we weren't erasing it at all, right? But if we don't go there, then we get to the scan, we put the new watch, which is the same structure, 3 and not C, into location C1. C1 is now the not D, right? So we swapped a second time right here, C1, CK swap. And then we put the watch that we have here, which is 3 not C, onto list the negation of D. Well, D, not the negation of D, the negation of the first slot. So this is negative D, so the new one would go here on positive D, right? So it would then insert, I guess I'll keep it red. It would then insert 3 not C here, and it's going to erase it from here. Because now C and D are in the first positions. But here's where I'm a little confused. It doesn't look like the watch in this spot got rearranged. And now the B isn't in the correct spot. So what did I miss along the way? It seems crazy to me that it could possibly be correct the way I'm understanding it. There must be a step in here that happens a little different than what I drew, right? Because if I were to, see, I'm propagating this. I might get to the end of propagating that and guess that C is true. It would be a weird and bad guess, but I could guess that. And it shouldn't lead to any bugs if I did. But then it would process this and assert that there was supposed to be a B in one of these spots. And there's not. So that's why I'm confused about this swapping. Positive B negative C, negative D, right? Swap once, that goes there, that goes middle. Swap again down here, that goes there, that goes there. So let me go through all the code again. Make sure I've looked at this. Watches that we find is the watches attached to the not B, which is this 3 not C that I scribbled out pretty aggressively. The 3 not C there is the one we were iterating. We have a pointer there. It's not blocked. We generate the first swap right here when we find out that the positive B, which is the negation of negative B, the positive B is in the first slot. So it goes, okay, we'll swap that into the second slot because that's not a problem. It's just we need it to be in the second slot for the algorithm. Okay. And then we assert that that is how it ended. What is this? We put it in position 1. It's not true that the first literal here is not true. We scan the clause starting from here. That does not evaluate default since it's undefined. So we swap it with position 1, putting B there. this just feels wildly broken. Is there somehow a guarantee that if B got pulled off of this, that clause 3 would have B back up here again? Like, is it somehow possible that the only way... Because, like, right now, if you asserted D, you would have no problem, because you would find the not C and it would be good. But if you propagated positive C as the value, you would see that the B was in the wrong spot, and there's an assert that says that doesn't happen. Maybe if I walk through this piece of code, I'll be able to see something. Because I don't know if I walked through, like, specifically propagate while it was swapping things around. Because it seems pretty clearly like it's inserting a new watch. At first, it was maintaining the rule that each watch is a pair. It is a member of each watch is like a triplet of information with 2 copies, and then each of those copies has a little bit of redundancy removed because of the list that they live in. Right? And so you have 2 different watches for each clause, and that is still true. When I eliminate the clause for this, when I eliminate the watch for clause 3 here, it just pops back up over here. No problem. So the number of watches per clause stays at 2. The other assumption is that whenever you read a watch, it's one of those first 2 slots. And that does not seem to be true. And that does not seem to be true after the logic I just went through applies. So I want to figure out... When you go to next clause... It goes to the next watcher in the same list of clauses. Is there anything... Nothing down here immediately modifies the watchers again. Okay. Let's try using the debugger. I think I'll make one more attempt at making sense of this by using the debugger, and that'll be about all I have time for today. So if we use the debugger and something clicks, then might update the picture that I drew. But if it's still dumbfounding, then we'll just stop there, and we'll call this the end of the day, and we'll have to pick it up again next week around the same time, maybe on Friday or Thursday though. Okay. Debugger. Where is the propagate function? It's in solver 500. Okay. I want to see that line. We don't expect the blocker to be true early on. We might see it swap here. Yep, that might make sense. By the way, what's the clause number we're looking at? Clause number 228. And the false literal we're looking at is 0. So the positive literal we're looking at must be 1. Okay, so we started by guessing that the first variable is false. If the 0th watch is true, then the clause is already satisfied. That can't be true because we shouldn't have any more information. The only thing we should have so far is that first guess, and so there should be no way for something to evaluate to true yet. In fact, this should be equal to the blocker, based on my understanding. Yeah, there's no way that those are off yet. Okay, so the fact that the first isn't necessarily equal to the blocker is interesting, because that implies something that I was overlooking. So that implies that maybe this could show up, and we would treat that as the blocker, and it wouldn't be a problem. What do you guys think? Let's think about this. There it is. Got it. Got it. Take a look at this. So when I was thinking, oh hey, it asserts right here, I was thinking that that this assert meant something like, if I'm processing this watch here called 3B, that watch must be, that B must be one of the first two for it to work. But that's not what's happening. So my understanding of this was overly simplified. So this here implies to us the following information. We're talking about clause 3. Since we're in the watch list for positive C, we're expecting to find a negative C here or here. And there's a blocker on this watch called for literal positive B. The blocker does not have to be here. The blocker will be somewhere in this clause, but it is not necessarily in the first spot, right? The ones that have to be in the first spot are this one, and so negative C and negative D, because that's the implied thing here and here. So now we have clause 3. In this watch list, this watch implies that we're talking about clause 3. It tells us, hey, clause 3 contains a positive B, and also since we're in the positive C list, you know it contains a negative C. And since the watch is in this list, the negative C has to be one of the first two, because there are 2 watches per clause, and those 2 watches have implicit information about what's in the clause based on which list they live in, right? So which list it lives in is relevant to these first 2 slots. These first 2 slots tell us which lists we'll find the 2 clauses in, right? They go together, but the blockers don't have to. And so the blocker is free to be some other thing, and it's sort of a freebie, I guess. It's like, if we didn't have the blocker, what would that look like? We would not be able to do this extra check. We would not do this because there'd be no, that's just like making sure we're not doing redundant work kind of thing. We would check the value of the first thing here, and if it was true, we would then just say, oh, well, then first is a blocker, right? We would stop saying first is a blocker. We would just say, okay, well, fine. We put a watcher back in this list for clause 3 again. Right, we're maintaining that pair of watchers. And then we look for a new watch. Here, all we would do when we find a new watch is we'd be saying, hey, the new watch is better because it isn't false. I'm not sure why that makes it better, but it's better because it's not false. And so let's replace the one we just processed with this new one and save the new one into the list in the right spot. So we would still be tracking a pair of watches for each clause, and that pair would match the first 2 slots here still just fine. All a blocker does is give us an extra accelerator here that can be outside of those first 2 things, right? So if for instance, we've already assigned B not true, and so by processing the B not true case, we swapped that out. And we said, okay, it's more interesting. It's more interesting because this was set up so that if B not true gets processed, this watch, what this watch is telling us is when B is not true, you want to process clause 3. Interesting. You want to process clause 3, and you want to process it in the following way. We know B was one of the ways to make this clause work, and you just negated that possibility. So let's get B out of the first two, and let's put something else in there that has a chance of helping. So the not C, which we had here, gets preserved somewhere else, and a new literal from the clause takes this position, and that new literal that takes this position tells us, it has the property that, one, it's not already false. So if it's true, then it just takes the clause out of the running for things we are got to be concerned about at all. And if it's undetermined, then it gives us something to maybe set to true. But if it was false, it would be just as useless as B. Anything that's already false, we shuffle back it farther in the list, because those aren't things that can help us make this clause true. And we keep these two as sort of our best bets, right? We're keeping them sort of to the front as best bets for how to satisfy this clause. And the blocker there is just like an extra piece of information that is getting tracked along, so that you have a chance. I don't know how often the blocker gets hit. I'd be curious. It'd be interesting to make. You know what would be interesting to do is to make an animation of these algorithms rather than trying to code them directly. It'd be interesting to figure out how to animate them. Okay. Oh man, I'm fighting off another sneeze. Okay. Yeah, so if we get to the end of that, there was no clauses, then it says this clause is a unit under assignment. So how is that to be understood? Well, we're doing propagation. If ultimately we get to a point where we've scanned a clause and all of its variables, all of its literals go to false, then we have a conflict clause. And so then we got to go that way, right? And we finish up the loop by just saying, save all these watches. We don't want to lose watches. We're trying to maintain constantly this machinery where there are 2 watches for each clause, and they live in these lists that correspond to the first 2 literals of each clause. We did not find a watch here, so the goto didn't interrupt this. And that leads us to just saving the watch we got. Okay, right. That makes some sense. So we say here's the watch that would be appropriate right now to write out in replacement of the one we read in. And the one we write out here goes into the same list if one of these is already, if the first one is already true, then we don't modify the list. So I don't know exactly what that looks like. That'd be a good spot where the animation could help. But if we got this far, it means there were no variables past those first 2 that were undetermined or true. And so this clause is close to being critical. We also have that the very first one that we, like the way we got here was through this assignment that we're processing, right? So this all started when we were processing the fact that we've assigned a particular value, right? We've asserted a particular literal as a fact, and so the watches that we found associated with that literal are all the clauses where that literal now evaluates to false in one of the first two slots, right? So one of the first two slots is false because it lines up with P, and we put that in slot 1. All the things past slots, the first slot is not true because we would have found out about that here. All the things past slot 1 and 2 are also false. So what do we have? We have the slot 1 is false, slot 2 and beyond are false. Slot 1 is not true, so there's only two possibilities left. Either slot 0 is undetermined, or slot 0 is false. If slot 0 is undetermined, then we're determining it right here. Right? We're saying this literal needs to evaluate to true, and this is the clause that led us to that conclusion. And if we find out that that literal is already evaluating to false, then we say this is a conflict clause. We need to run conflict resolution. So that makes sense. I think I get that now. And what's cool about this algorithm is it's using that pair of unique spots to shuffle through all of the literals in the clause. Anytime it's got a false one, it demotes the importance of that and starts sending it to the back of the clause. If it's got a true one or an undetermined one that it can swap into the front, it wants to do that, right? So it tries to find ones that are not already false to swap into the front. But it's not a perfect machine. It is not constantly updating all the time. So it's got these pairs that it's keeping lined up. And sometimes there might be stuff that's true later on, like literals that are true later on in the clause that haven't been found and shuffled to the front yet. And there might be things which are false near the front that need to get shuffled back, right? So it's sort of incrementally moving in that direction through the process in such a way that it does turn out to make progress or find out that this clause is satisfied when it needs to. Cool. Okay, so I understand how it's doing propagation. I'm going to wrap up there, like I said, and I still have a couple other parts I didn't understand. I don't understand the redundancy check at all, and I think that's another big thing I'd love to wrap my head around if I can. And now that I understand the watches, I think that will be more possible. But that'll have to be a project for another time. And maybe what we'll do, not for sure, but maybe what we'll do is after I've read the redundant check code and understood it and maybe drawn a picture of it, maybe we'll play around with how to animate an algorithm like this so that we could visualize it as it's running more effectively. I feel like that would be fun. But anyways, that's all that I have in the tank from streaming today. I need to go rest and recover from these allergies. It's a nice day outside here, but it's also hitting me hard, so I don't know if I'm gonna go outside and enjoy it or try to figure out some way to minimize the impact of the outdoors. But I gotta do something besides sitting here on the computer, so I'm gonna go do that. See you guys.